Okay, so let's continue. Last lecture we were saying that the discussion that we'll have regarding amplifiers will be in the context of a particular design where the specs are that voltage gain is greater than 100, 3 dB frequency more than 1 megahertz, output swing plus minus 3 volt, load resistance is 1K, and as I said, everything has to be designed keeping in mind 0.5 micron technology. And in any design, we have to make our circuit insensitive to supply voltage variations and temperature and other things, right? So, all right. So the parameters are given here. Anyway, so let's start. As I said, the first amplifier that we take is a simple common source amplifier with a resistive load here. Okay, resistive biasing, and you have you can make it using a P channel as well. So in this case, we have an N-channel MOSFET here. This VG is used to bias this particular MOSFET in saturation region or above threshold. And VDD supply voltage, as I said, for us is plus 3.3 and minus 3.3. This is a single supply amplifier. So we have used only one supply voltage. We could have also put here minus 3.3 as well. So that would be a dual supply-based amplifier. All right. So as usual, any amplifier that you have schematic, the first thing that you do is DC analysis. So DC analysis is straightforward here. We are assuming that the transistor is biased in saturation region. So we have an expression for current in saturation region here, and VGS is given to us. So for as an example, we've taken 1.2 volts. So you plug 1.2 volts here, and the size is not indicated, but we are taking size, let's say, as 2 by 1 here. And size is here indicated 2 by 1 in the transistor here. So you can calculate beta N, and VGS is known to you, so you can easily calculate what the bias current is. Q denotes the quiescent current, quiescent point of the bias point. Okay, so we get the yes.
Ratio 2 by 1.
Yes.
So we include that WD and
yes. Ideally speaking, you should include that. Yes. So Kp W effective divided by L effective, and that's how you do it. Okay. Lambda, you can include lambda, but remember lambda is a small parameter. So, for example, one would have done here 1 plus lambda VDS, but it's small, so it doesn't cause too much of an error in IDSQ. Remember, all these equations are simplistic. If I actually take a B-symmetry model and put 1.2 volt here and 2 by 1, I'm not going to get 20 microamperes. I'm going to get, some higher value or a lower value depending on that. So these are just approximate numbers, just to get started. Okay, 1 plus lambda. There's no point in doing a very accurate calculation when this whole equation is not very accurate to begin with. Okay, all right. So once I have IDSQ, then all we need to do is write a KVL in this output loop here. So we have VDD minus IDSQ times RD. So we get the drain to source voltage here, and that is 1.29 volt here. And we note also that once we have VGS as 1.2, so one can calculate what is VD sat, which is VGS minus VT. And this comparison is needed to ensure that my transistor is in saturation. We assume that transistor is in saturation region and use this particular equation. I need to check whether this is indeed true. So VDSQ is in fact greater than VD sat. So this is fine. My use of this equation is fine. So DC analysis is pretty straightforward. Not much to do here. Next thing is small signal model. So what we do is replace the transistor by a small signal model here. And of course, as you all know, the voltage will become a short, and this voltage will also become a short, and the small signal voltage for us is this VDD here. So that's the small signal model here. We are doing a low frequency analysis first. Okay, so none of the capacitors have been put here. So all the capacitors have been removed, and so first thing is to use the small signal model, I need to know what is GM, what is GMB, what is R0. So, and these GM and GMB and R0, they all depend on the bias point here. So these are the equations that you guys all must know. GM is square root 2 IDSQ times beta, so one can calculate that. One can calculate R0, 1 by lambda IDSQ, 3.3 mega ohm here. GMB is GM times eta. Eta expression is given. Go back and look into earlier notes. Expression is given, so one can calculate GMB also. Anyway, we don't really need GMB because body in this case is also connected to ground. So VBS is 0. So it's not really required, but nevertheless, these values have been given to you just so that you know what the typical magnitudes are. Okay. So R0 is in mega ohms, GM is in, 60, 70 microamperes per volt, and GMB is maybe a factor of 2 or 3 smaller. Okay. All right. So what we are going to do is take this particular model, put it back into, substitute the transistor with this particular model, and we have a small signal circuit which we can solve to get all the values that we want here. Okay. So I'm drawing the small signal circuit. So Vn is here, and of course this is shorted. It's replaced by the transistor model, replaced by RD. This is ground, and that's the small signal circuit that you get. And these are straightforward circuits, simple circuits here. One can easily write, if you note here, V0 equal to GM, VGS is nothing but Vn, GM times Vn. This is a current which flows through a parallel combination of R0 and RD. Okay, so one can write V0 as GM, Vn, RD parallel R0, and therefore the gain one can write as GM, RD parallel R0. And you will see, for example, the value that I've given here is 100K, and 100K in parallel with a mega ohm, 2 or 3 mega ohm, you can neglect the effect of R0, and it's simply equal to GM RD. Okay, and you can show in general, some of you may want to do it, show in general that if I have a circuit like this, I can always make an assumption that RD will be much smaller than R0, at least an order of magnitude small. I don't need to go and take a typical value of 100K. You can show that RD in a circuit like this, RD will always be much smaller than R0. Okay, try and prove that. And so anyway, AV is minus GMRD. Look at the value here. Even with the 100K resistor, I get 7.9. That's all. A voltage gain of 7.9. And also note, so the magnitude is relatively small. Also note the negative sign. There's a 180-degree phase difference between the input and the output. Okay. All right. Our output resistance R0 is 3.3 mega ohm. Anyway. All right. Output resistance. Well, output resistance, as all of you know, what you need to do is a general method for finding output resistance is remove the input, apply a source from the output here, Vx, and look at the current Ix flowing in, and Vx by Ix will give you the output resistance. And that's the general method. And so when we put VGS, when we remove the source, this current source becomes open circuit, and you can easily see that Vx by Ix is simply RD parallel R0. Okay, is RD parallel R0, so which is simply equal to RD 100. All right. So output resistance of this circuit is simply the resistor that you put here. Okay. Input resistance I don't need to consider, which is infinite. Okay. All right. Next thing is, so what we are doing is we have taken this very simple amplifier. One by one, we are looking at all the important specs. Voltage gain, input resistance is infinite. We just saw output resistance. Let's look at the output voltage swing. How large is swing? So the issue that we want to know is how large can the AC amplitude of V0 be? How large can it go? Okay. All right. So this particular diagram shows you that I have biased it at. This is showing V0 here. Okay, V0 versus time, and Vin is 0.1 volt. So now because Vin is 0.1 volt, what is happening is, as I explained in the last lecture, because of the sinusoidal voltage, there is a sinusoidal current, and because of sinusoidal current, there is a sinusoidal voltage here. So note that the sinusoidal voltage is riding on top of a DC. Right? There is a DC value here at this point, and sinusoidal voltage is riding on top of that. Okay, so we said that there is a 180-degree phase difference. So as this voltage for a positive cycle, we get a negative cycle, and for a negative cycle, we get a positive cycle. So the issue now is how large can my output voltage swing be? Now you see the consequences. How do I increase the output voltage? By increasing the input voltage. So as I keep on increasing the input voltage, the output will keep on increasing. Now note, when I went from Vin equal to 0.1 volt to Vin equal to 0.3 volt, see what happened. You can begin to see some problem occurring here on this side here. Why is this occurring? Huh? Non-linearity is there, but what is the source of non-linearity? Cutoff or saturation? No, it is already, I want it in saturation. Okay, forget about bipolar. Bipolar, you don't want the transistor to go into saturation. MOS, you want it to operate in saturation region. So what is happening here? So note that what is happening is the effective voltage across the transistor is decreasing, right? On the negative side, the effective voltage decreases, and as the effective voltage decreases, my transistor enters into triode region. Why should distortion occur when it enters triode region? Because triode region, remember, what happens is output resistance is very low. In triode region, output resistance is low. And output resistance is low means what? Why is the output resistance low? Well, how should you think about output resistance? Well, if you note here, this is ID versus VD. What is output resistance? 1 over inverse of the slope, right? So the slope is pretty, R0 you can see here, R0 is pretty high, but the moment you enter triode region, R0 becomes small. And remember what is the gain? Gain is equal to minus GM RD parallel R0. So here R0 in saturation, R0 was large, we could neglect it. But the moment it enters into triode region, we have R0 which becomes small, and which means gain becomes small, right? Gain starts to decrease. And if gain becomes small, what does it mean? That V0 becomes small, because V is same, so V0 becomes small there. So that's why you begin to see some saturation occurring there. Now, saturation of the voltage waveform, not saturation of the transistor, okay? Please keep these terminologies in mind here. So it's beginning to, the transistor is entering into linear region. So one thing that you have to keep in mind is, if you want to avoid distortion, you have to keep the transistor out of linear region. You have to make sure. The moment it enters into linear region, you'll start seeing this kind of a clipping. Alright? Okay. So what we are going to do is, this particular circuit, actually, if I look at 0.1 volt, it appears to be a reasonable sinusoid, right? But it's not the visual check which you should perform. What one can do is, for example, take this sinusoid, which appear waveform, and I can do, let's say, an FFT on it, which will give me a spectrum. What you will find is that this is not a pure sinusoid. I will see here that apart from a fundamental, there's a second harmonic also. So distortion is always there. Remember, the view of distortion that we have is harmonic distortion. So distortion is present even here. At this point, we have to calculate how much distortion is there. Second harmonic distortion will be present here. The only thing is, as you keep on increasing the output amplitude, eventually it starts going into triode region here. And then now the distortion has become visible. You can begin to see clipping and all. Okay. So what I'm trying to say here is, first of all, what we'll do is find out the absolute limits of when the distortion becomes visible, visibly large. Okay. So those absolute limits of output voltage is what we're going to try and find. So this is one limit that you see here. Okay. And that, as I said, is because it enters into triode region. Let me skip all of that here. Okay. Oh, all right. So this particular diagram here that you see here, it shows how output voltage here changes with input voltage here. Okay. And so basically what happens is, as you increase the input voltage to larger and larger, you can see our output voltage becomes smaller and smaller, and it's entering into triode region here. So this is a this waveform that you see here. It shows VDS as a function of VGS. Focus on, let me draw it here. Okay. So this one, it shows you for the same circuit how drain to source voltage varies with gate to source voltage. Okay. Look at this wave circuit here. All right. In this circuit, I'm asking what is the drain to source voltage as a function of gate to source voltage. Assume that, let's say, Vin is not there. There's only VGS which is present, and I'm changing VGS. Okay. I'm changing VGS and I'm looking at VDS here. So this red curve shows you how VDS varies. So remember what my VGS value was, around 1.2. So I was biasing it somewhere here. Right? Now when you apply an extra input voltage, what would happen is your transistor may go a little bit here on this side, and then will go a little bit up there on that side. Right? So VGS will vary. So you're biasing it somewhere here. But note that as the gate voltage becomes larger, your transistor is going into triode region. As the gate voltage becomes very small, the transistor, what happens here? It goes into cutoff here. So this is the region. If you look at your drain to source voltage, you see that there is a region where my drain voltage is not responding to gate voltage. Not responding to gate voltage. Gate voltage is changing, but it's not responding. Then it starts responding, and then again, it doesn't respond. It doesn't respond because it has entered into triode region. So obviously now if you take your MOSFET and you bias it here, if you bias it at this region, it's not going to respond, right? There's no change in VDS. Remember, VDS is where you take the output. So there's no change in VDS, there will be no change in output here. So you're not going to get much gain here. Similarly, if you drive it here, again it will not work properly. So note that you have to be somewhere here in this region. This is the place where the VDS is varying rapidly with VGS. So if you want gain, you have to be somewhere here. But note that wherever you bias, if you apply a large enough voltage, it's going to go into this region. Or it may go into this particular region. So, and that's where you will begin to see a visible distortion. When it enters into this region here, you will see clipping. When it enters into this region here, again you will see clipping. So two clippings you may see. This clipping you will see on the upper side, this clipping you will see on the lower side. So you can see why clipping is up. The transistor is entering into subthreshold or cutoff region, or transistor is going into triode region. So these are the two things that you have to worry about. Transistor should not go into triode, transistor should not go into cutoff. It should be in this region here. Now this region also, please see that it's not linear. It's not linear, which means a change in VGS will cause a change in VDS, but the change will not be linear, will not be proportional. And so even if you are in this region, there will be distortion. Okay? Alright.
The current is one square for some value of VDS, and then the saturate with respect to VDS.
The current is? Yes, the current increases with VGS like a square, and then after a while the current doesn't increase with VGS, it's going into triode region. It goes into triode region. Okay? So that's where there's an absolute limit on how large a current you can go. That's decided by the supply voltage. Because supply voltage is fixed, so you can't have any value of current. Okay, so that's what so the first thing, if you go back to this picture here, distortion was occurring because it was going in triode region. In the next case, for a different biasing condition, distortion is occurring because it's going into cutoff region. That's where you see distortion here. You can see the sinusoid. One way of seeing a distortion is look at the negative amplitude and look at the positive amplitude. You can see a huge difference between positive amplitude and negative amplitude. Positive amplitude is smaller, considerably smaller than the negative amplitude, and which is showing you that it's having problems on this side. Okay. All right. This is the picture that we will use for calculating what are the hard limits on output voltage swing when the distortion becomes visible again. Try and understand this particular picture. What I've drawn here is a upper supply rate. My voltage cannot exceed VDD. On the lower side, I've drawn ground. My voltage cannot go below ground because ground is my lower side here. If this had been minus some 3.3, I would have put minus 3.3. In this case, it's ground. Now, this is where I've biased my transistor. VDSQ, I've drawn a line indicating the biasing point here. So drain to source voltage here, VDSQ. Okay. So we understand that. On top of VDSQ, as I apply my input voltage, I would have a voltage like this. That's the output voltage. Sinusoidal output voltage here. The blue dotted line that you see here is the sinusoidal output voltage. Net voltage at the drain is what? This plus this here. So that's the net voltage. Okay. Now, what I've drawn is a region here, shaded region here, which is a forbidden region. Your transistor should not enter this forbidden region because, and what is the extent of this forbidden region? VD SAM, VGS minus VD. If your transistor enters here, which means if its drain to source voltage enters into this region, it means it is in triode region. So the shaded region is like forbidden. Don't let your transistor enter into this region. On the upper side, we have not put. We have said it can go as much as VDD. But, it can get very close to VDD. All that happens is, note that as V0 gets closer and closer to VDD, the net current becomes smaller and smaller. So it's gradually entering into subthreshold now. So we have not put any shaded region and all that there. We are saying it can go up to as much as VDD. Okay. So now, if you look at this picture, What are the limits on V0 now? There are two limits. I can get limited in V0 by the upper half, which means that this peak here in the positive peak starts touching VDD. So I can have that limit, or my negative peak starts touching starts going into the forbidden region. So what are the limits on my V0 max? One limit on V0 max, as you can see, is VDD minus VDS. That's one limit. I can't have output voltage which is larger than this. That's an upper limit. Output voltage will always be less than VDD minus VDS. The other limit is output voltage will always be again less than VDSQ minus VDSAT, because the moment I enter into this, I'll get visibly large distortion here. Now, which one will actually determine my voltage swing? Whichever one is smaller. Okay, so actual voltage swing would be minimum of V0 max 1 and V0 max 2. That's the one which is going to determine. But remember, these are the hard limits. As I said, even before it touches this, goes into this forbidden region, there is a harmonic distortion. And for your application, even before it touches this, the harmonic distortion may be too large. It may be unacceptable. So these are, what I'm talking about is, these are the absolute limits on V0. For very few for hardly any application, you would go beyond these limits. Okay? Alright, so these are so this is the kind of a diagram that you need to draw in general for any circuit that I give you, and you want to find out what are the hard limits. Note that there's an upper limit here, there's a lower limit here, you don't want it to go into saturation region, and then you draw this diagram and figure out what is the constraint on positive swing, what is the constraint on negative swing. And whichever one is smaller will actually determine what the overall swing is. So let me, so you can see from this particular diagram, we know what is the constraint here. The constraint is from, if you bias it very close to VDD, the constraint is on the positive swing. And so V0 would be determined by VDD minus VDSQ. If you, on the other hand, and this is this particular situation, note that distortion is occurring here on the positive side here. Okay, visible distortion because it's touching here. In this case, if you bias it close, then the limit will be VDSQ minus VDSAT here, and you can see here clipping is happening on the side here. Okay, so depending on where you put VDSQ, either this limit or that limit may become more important. And all of you know where it is heading. Where should you put it for maximum swing? As most of you have heard, that you should put it in the middle. Okay, so optimum drain source bias. So I have, this is so you should place it such that the upper limit is equal to the lower limit. That would be the optimum point. So you put VDD minus VDSQ is the lower limit, and VDD minus VDSQ is the upper limit. VDSQ minus VDSAT is the lower limit. Equate the two, and it tells you that the optimum biasing point is VDSQ is VDD plus VDSAT divided by 2. So that's where you should bias it. People, you know, if VDSAT is small, people generally tend to bias it in the middle of the supply range. So if you neglect VDSAT, if you want to do a very simple calculation, then it says VDSQ is VDD by 2. So bias it in the middle. So if you have 3.3 volt, bias it somewhere close to 1.65. Okay. All right. So in this case, for the example that we are looking at, say if this is 70K, VDSAT is 0.5, VDSQ, then if you bias it at 1.2 volt, note if you bias it at 1.2 volt, VDSAT is 1.2 minus 0.7, so it's 0.5. So VDSQ should be VDD plus VDSAT by 2, so which it should be 1.9 volt. And so if it is 1.9 volt and VGS is 1.2, so we have 20 microamperes. So it tells us what value of RD you should choose. Okay. So once you decide the gate voltage at which you should bias, right? So here we have decided that we are going to bias it at 1.2. On what basis have we decided 1.2 is not clear at present. That's a choice that you have. But suppose you decide to bias it at 1.2, then if you want to get the maximum output voltage swing, then it tells you how you should choose RD. Because once you decide to bias it at 1.2, 1.2 decides VDSAT, 1.2 decides the ID, and then you know what is VDSQ from this here, and then it tells you what value of RD you should choose. Alright, so for maximum swing, RD should be 70 kilo ohm, and what you should get then is, so this is the picture that we have here. Biasing is at 1.9 volt here, This VD sat is 0.5, and you bias it in such a way that the upper swing, positive swing, is same as the negative swing, which is equal to 1.4. Okay. So if I go and build this amplifier, how large a swing should I get? Or peak to peak 2.8, or swing of sinusoidal peak voltage, maximum voltage, I should get 1.4, right? Okay, so let me show you now. I'm not going to build, but I'll simulate it. Okay, so I should get 1.4 and peak to peak 2.8. All right, let's see if I simulate it, what does it show? Will it show 1.4? All right, why? That's what it shows. Okay, so let's look at this graph here. So it is biased at close to 1.9. Okay, now I have applied some input voltage. Okay, how much input voltage we'll see in a minute. But look at now what is happening here. At some input voltage, this voltage, do you see distortion? Visible distortion? It doesn't look like a very nice sinusoid, right? Already. Now, if I look at the peak value here, 2.914. 2.914 minus 1.9 should give me the positive swing. And this one, the voltage here is 0.506. And this 1.9 minus this should give me. So let's see how much it is. This one is 1.06. And this one is 1.35. So we just saw that I should have been getting 1.4 and 1.4, and I'm not getting it. Why?
What is the gain of the amplifier because of which the input gate voltage is also fluctuating?
No, gate voltage is fixed, and gate voltage once I biased it at 1.2 or so, and then sinusoidal I'm applying.
Yeah, so if suppose the gain of the amplifier is not that much, so your small signal would not actually, the small signal sinusoid that you have applied at gate voltage would not actually be very small.
Fine, it's not very small.
If it is not small, then your gate voltage is fluctuating, so your VDS in short is fluctuating. So that 0.5 region is actually not 0.5.
What you are saying is what you are saying is this limit here that you see here is not 0.5. More than that, you see the problem is not so much occurring here. The problem is occurring on the higher side. In fact, this is not bad. We were saying it can go up to 1.4. It's going up to 1.35. That's not bad. You are raising a valid point that I'm saying my triode region begins once it enters this particular region. And my shaded region was calculated on the basis of a particular gate to source voltage. But then gate to source voltage is also changing, as you're rightly saying. So this shaded region is also a little bit increasing, decreasing and all that. But that's not too much. That's not too much. You're right, but that's not too much. But major problem is, I would have expected this to go to 1.4, or if this were 1.35, it only goes to 1.06. Huh? Which one? R naught? No, R naught is not an issue. Huh? So this is the point that I'm trying to say. These limits that I have drawn here, these are absolute limits, 1.4 and all. Even before you reach, there is a lot of distortion you can see here. It's a fairly distorted sinusoid. I have 1.06 is a positive part here, and 1.35 is a negative part here, right? It's a really distorted sinusoid. In a real sinusoid, I would have expected if this is 1.35, maybe if this had been 1.34 or 1.33 would have been an okay sinusoid. But this is 1.06. So what has happened is, this is what I'm trying to tell you is, most of the textbooks and all that you will read, they'll say, okay, maximum swing is 1.4. This is the level of discussion that you'll have. Maximum swing is 1.4. And then you go and build an amplifier in the lab or you simulate it, you'll not go to 1.4 at all. You'll never reach 1.4. It will be very hard to reach 1.4. Even at 1.06, you are seeing it's so distorted. So you may say, well, let's apply even larger input voltage. Let's see where it goes. Let's see if I have even larger. Okay, so in this case, peak to peak, I don't have an input voltage here. I don't know how much input voltage I'd applied. So peak to peak swing is 2.4, which is 0.4 volts smaller than the expected value. In this case, I applied a lesser input voltage, smaller input voltage. Now you can see sinusoid looks reasonable, not that bad. Positive swing is 0.93. I mean, still 0.93 here, 1.275 here. Would you say it is a reasonable sinusoid? No, you are not happy even with this sinusoid. So how large a swing do you think I can get now? I'm not even getting 1 volt swing. I'm not even getting output voltage swing, which is 1 volt. Okay. So the point is that again, that what I'm trying to emphasize is these diagrams that you draw, they're just telling you what is the theoretical maximum here and theoretical maximum here. Actually, all that you're seeing is even 1 volt is becoming difficult to get for you. Even 1 volt swing is difficult. Because I've lowered my input voltage and still this is 0.93 and this is 1.275, which means distortion is significant even at this stage. Okay. So the issue is, how large a swing do you think you can get? How should I answer that? For this amplifier, what is the swing that you can get? Would you call a swing of 1 volt is what you can get? How should I define the output voltage swing?
Peak to peak.
Fine, I can define peak to peak, but what is this amplifier capable of? How much peak to peak? Is peak to peak 2.2 or is peak to peak 2.4? What is it? How much peak to peak? What kind of a peak to peak output voltage can this amplifier get? If somebody asks you for a number, right? We want a number of how much is the peak to peak output voltage swing. What would you say? 2.4, 2.2, 2, what? What value will you say?
So maximum voltage in at which the total harmonic distortion is less.
So the point is the specification of peak to peak output voltage swing is incomplete until you specify what level of distortion. So you say I'm getting a 2 volt peak to peak swing at a harmonic distortion of so much. Then only your sentence is complete. There's no meaning in saying my peak to peak swing is 1 volt. Right? If somebody says peak to peak swing is 3 volt or 2.5, there's no meaning to that unless you specify how much harmonic distortion you get. Then only your sentence is complete and all that. So the point that I'm trying to say is these are the hard limits, 1.4 and all that. These are very quickly to say, well, my amplifier cannot give me more than 1.4. All that I can say is can't give me more than 1.4. But a finer discussion is required as to how large a swing can my amplifier give. And to do that, I have to go into a discussion of distortion. Yes.
Sir, all these simulations show that it usually fails at the upper limit. That is, the transistor is reaching cutoff way before then.
No, that is because of the way I bias it. If I had biased it differently, it would have gone into triode region. It all depends on my biasing. It depends on which limit comes. Okay, so it depends on that. All right. Okay, so all that is something similar is what I pointed out, that if you look at VDS versus VGS here, the curve is not linear. And if the curve is not linear, there is always harmonic distortion. And harmonic distortion will be small, as you can expect. If I bias it here, let's say here, if I stay very close to it, signal amplitudes are small, harmonic distortion is small. As the signal amplitude increases, harmonic distortion will increase. Okay, so let's do a calculation of harmonic distortion here. So this I've already explained. Harmonic distortion is specified as the first or the second or the third, whichever harmonic distortion you're talking about, depends on the amplitude of that harmonic divided by the fundamental A0. Okay, and you can sum these harmonic distortions in an RMS manner, and you get total harmonic distortion. Okay, so let's calculate harmonic distortion then, because without that we cannot specify what the output voltage swing of my amplifier is. So the way I'm doing it is as follows. Note that this is the fundamental equation of a transistor biased in saturation region. Now what I've did, we've done that earlier also. If you want to find out, so apart from the DC, this is small, VGS also attached to it. So we have added VGSQ plus VGS minus VT. And as a result of this VGS, which is nothing but input voltage, there is a small IDS also there. So apart from the bias point, there is a small IDS also. So that's the fundamental equation, and one can rewrite this particular equation as IDS. I can simplify this and I can write it as IDS equal to GM VGS. Note that DC values are all in capital letters and sinusoidal values are all in small. So IDS is GM VGS plus 0.5 VGSQ minus VT GM VGS. Small signal approximation is basically what is it doing? Neglecting the second part. It's saying VGS is very small and neglected. But then the moment I neglect it, then I get a linear relationship and I get no distortion. So when I'm talking about distortion, I cannot use the small signal model. Small signal model implies linearity and no distortion. So any estimate of distortion you can only get if you go back to the original model, which does not make the small signal approximation. Okay, so that's why I had to go back to this expression and write it here. So let's calculate an estimate of distortion. So IDS is GM VGS 0.5 VGSQ minus VT GM VGS square here. So what I'm calculating is the following. What is the distortion in IDS? Sinusoidal IDS. Because remember, how does amplification take place? Is the gate to source voltage VGS, right, which is a sinusoid. What does it do? This VGS generates a sinusoidal IDS. And the sinusoidal IDS flows through a resistor and generates the voltage. So there's no distortion from IDS to V0. If you want, I can write down my amplification like this here. I have VGS, small signal VGS goes to IDS, and then this IDS goes to V0. Note that this relationship is linear. V0 is nothing but IDS times RD. So this is linear. No distortion occurs here. Distortion occurs because of this part here. Okay, that's where the non-linearity is. So that's why I'm calculating what is the distortion in IDS. Whatever is the distortion in IDS, same distortion will be in V0. Okay, there's no difference between the two. Alright. So now how do I calculate distortion? VGS, I'm going to write it as sinusoid. VGS is equal to A0 sine omega t, and plug it into this expression here, and we get simplified. We get a first fundamental here, and we get a second harmonic here. The ratio of the second harmonic versus the fundamental will give me the harmonic distortion. So in terms of percentage, HD2%, we get A0 by 4 VGSQ minus VT into 100. Okay, so that's the harmonic distortion. That's the expression. So what it is telling is, remember for the example that we are looking at, our VGSQ was 1.2 volt, VT is 0.7, so this is equal to 0.5. So if I plug 0.5 here, and suppose your application is such that the maximum harmonic distortion you can tolerate is 5%, then it is telling you, if it is 5%, then it's telling you A0, the input magnitude has to be less than 100 millivolts. And if your gain of your amplifier is 10, then it's telling you 100 millivolt multiplied by 10, the amplitude is, maximum output amplitude is 1 volt. So you're saying now, you're getting a limit on output swing from where? From how much harmonic distortion you can tolerate. Depends on your application. If you have a very high, higher end application, you really want to listen to some nice music, and so you want to HD2, you want maybe 1% or even less. So you have to put here HD2 1% or 0.5%, right? And if you put HD2 0.5%, what does it require? Very small value of A0, and if the gain of the amplifier is 10, so it will tell you very small value of V0. So how large an output voltage swing you are seeing is related to what value of harmonic distortion you can tolerate. The two are linked together. Okay. All right. So let's do that. Let's calculate output voltage swing now, determined from harmonic distortion here. So V in, as I said, is A0 sine 2 pi F0 t. HD% is A0 by 4. VGSQ minus V2 into 100. Note that A0 is nothing but the amplitude of V. When I write V in here, it means amplitude. Okay, not the sinusoid part here. So V in by VD sat into 25 here. So V in then I can write as, if you look at this equation, V in I can write as HD2 divided by 25 into VD sat. Now this is where an approximation I will make. I will say V0 is AV times V. Now note, this AV that I'm calculating, I'm obtaining from small signal approximation. Small signal approximation is not strictly valid here. Okay, so that's why one is writing here an approximate value, GMRD. So V0 then is equal to GMRD times V in. V in is here, so what we get is GM is also, I can write 2 IDSQ VGSQ minus VT here. So V0 I can write like this. V0, how large a V0 I can get in terms of harmonic distortion. So GM I've written 2 IDSQ VGSQ minus VT. VGSQ minus VT is nothing but VD sat. VD sat. So a simple cancellation here. So it gives you V0 equal to IDSQ RD HD2. HD2 is in percentage divided by 12.5. Okay. So you can, now there are various manipulations that you can do. IDSQ RD you can write in terms of VDD minus VDSQ. You can write it in that way also. Okay. So how large a swing can one get then? Well, one limit you are seeing is this hard limit. Another one you are saying is this, that it should not enter triode region. Another limit is being determined by the harmonic distortion, right? Whichever one is now smaller. See, if you bias it, if I take my VGSQ and bias it very close to VDD, let's say I buy VDD is 3.3 and I take VGSQ equal to and make it 3 volt. Now what will happen? If it is 3 volt, then this part will determine this. It will start touching that positive rail. Or if I take this and bring it very close to here, it will start going into triode region before my harmonic distortion becomes, this limit becomes important. Okay. All right. Sometimes, you will see in the notes what I've done is, so V0 max, if you look at, I've written VDD minus VDSQ, the positive swing. V0 max 2, I've written as VDSQ minus VDSAT plus 0.1. Why did I add 0.1? Why am I not writing VDSQ minus VDSAT? I mean, I've written, if you're looking at really a output voltage swing, I've added a safety margin there, 0.1 volt safety margin. Once it starts touching, then there's already distortion. Once it touches that particular, it enters into this triode region here, there's already significant distortion. So, this is not important, but if you want, if let's say you're designing an amplifier for a customer, then you better add some safety margin, right? Because you say, give me 2 volt and it starts at 2 volt, and note that there are variations in your transistor parameter. VT may vary, supply voltage may vary and all that. So if you don't keep a safety margin, the customer will feel cheated. You're promising 2 and, he's at 1.8 he's getting distortion. All right. So in a realistic design, all that I wanted to tell was you should build in some safety margins always to when you're calculating. So some safety margin here, some safety margin there. And all. So, now, okay, all right. So before we do that, look at these two equations. Look at this one here and this one here. Compare the two. So I've written 3 limits on voltage swing. This one from harmonic distortion. This one from signal touching the supply rail, this one from triode region. If you compare the second one with respect to the first one, what do you see? When is this equal to this? When harmonic distortion is 12.5%. No, that's a very large harmonic distortion. For typical applications, you may have 5%, 2%, 1% or something like that, or lower. Which means that under most circumstances, what I will have is this limit will get violated before you reach this. Okay. So realistically speaking, then you should take this as a limit and this as a limit. These two. You don't need to bother about this one. Because what would happen is, again, before this you reach this limit, this one will, in most applications, will get violated. There may be some application, for example, if you're driving a motor, let's say, and in a motor, maybe it doesn't matter that it's a perfect sinusoid. Right? Perfect sinusoid, maybe, then maybe go ahead and drive it as close as to this. Maybe you don't bother about HD2 at all. Even a square wave is fine for a motor. Let's say for some application I'm saying. Then it's okay. But as I said, in most cases, what would happen is this limit will get violated before this one here. So what you need to consider then is only these two limits. As I said, the moment you reach 12.5 HD2 is a large distortion. No, this equation itself will not be valid. Every equation has a range of validity. Okay, so this equation itself will cease to. Remember, all this equation is based on, for example, I've assumed gain is equal to GMRD. When you have a distortion that large, gain is no longer GMRD. So that's what I'm trying to do, is say that this equation itself typically will use at 10%, 5% or lower distortion. Okay, and most applications may require you to have distortion less than that. So that's telling you is that this is one limit and this is the other limit. These two limits is what is going to decide your distortion. Decide your voltage swing. Okay, so we put this here. So V0 is here and another limit on V0 is here. Don't bother about 0.1 in exams and all that. Just put 0.1 equal to 0. Okay, so assume that this is not there. All right, then what is the optimum drain source bias then? Now note, these two limits are conflicting in nature. If you want to make V0 large, what should you do? For a given HD2, make VDSQ small. On the other hand, if you make VDSQ small, what happens to this limit? That goes down. Right? So these two are conflicting in nature, which means that there will be an optimum VDSQ. What will be that optimum VDSQ? Where the two limits become equal to each other. Again, it's the same thing. Because remember earlier, this term was not there. We had simply written VDD minus VDSQ. And then we were doing all our calculation. Now, this extra term has come. Okay? So we make them equal. We make them equal and then we do all that algebra here. It tells us what is the optimum biasing point. VDSQ. But now, earlier we were saying the optimum biasing point is simply in the middle. Now we are not saying it's in the middle. We are saying your optimum biasing point depends on how much harmonic distortion you can tolerate. Whatever your application is, whatever harmonic distortion you can tolerate, that will tell you what the optimum VDSQ is. And then, based on VDSQ, then one can calculate what is the value of V0 max that you have, maximum swing that you have. Okay? So these are a generalized expressions compared to the simple one that you have. If you want the simple one, all you need to do is put HD2 equal to 12.5. If you put HD2 equal to 12.5, it becomes 2 and then you go back to your earlier expression, the simplified expressions. Okay? And as I said, but for most applications, HD2 will have to be considerably less. Okay? So that's the optimum bias point. This is where you bias it. Optimum bias point for what? And this is a phrase that can be confusing. Optimum bias point for getting the maximum swing. Right? The word optimum could be, if your goal is to get maximum gain, this is not going to be the optimum bias. Okay? So this is optimum bias point for getting maximum swing. Alright? Well, now you can imagine that if I'm making an amplifier, let's say multi-stage amplifier. Say, here. When I'm looking at this amplifier, this stage, swing at this stage will be how much? First stage amplifier. See, signal is traveling like this, going from here, here, here. Is output swing important here? Note that, if all the amplifiers are running on 3.3. Where are you likely to reach 3.3? Here. If it is 3 here, and this has a gain of 10, so this becomes 0.3. And if this has a gain of again 10, this becomes 0.03. Swing is not an issue at all at the first stage. I should not bother about swing at the first stage here. So it's not an issue. So then I'm not going to bother about my VDSQ and all of those things. I'm going to then at the first stage, I'm going to decide, I'm going to bias my transistor so that I get a large gain, or my noise, as I said, first stage noise is very important. So I'll worry about those things. The swing I'll worry about here. Alright, at the last stage. I'll worry about swing at the last stage here, not at the input stage here. So when we say optimum bias point, remember optimum bias point from the point of view of swing. And that will be important only as I go to the output stage. Only at the output stage, not at the input stage. Okay? Alright, so let's do the calculation here. I'm showing you a kind of a sample design. Here I have 1.2, 2.1, and based on this expression, if so I've again biased it at 1.2 volt, and I want harmonic distortion to be 5%. Harmonic distortion to be 5%, and so I plug in 5% here. I get optimum bias point now as 1.38 from this expression, as 1.38, and IDSQ again based on the bias here, 1.2 volt bias, gate bias. IDSQ is 20 microamperes, and therefore I can get what is the value of RD. RD is 95.7 kilowatt. So I get a new design. Suppose somebody tells you, design a common source amplifier to give you maximum output voltage swing at 5% harmonic distortion. Then this is how you would go ahead and do it. 5% harmonic distortion is there, and on base of that you do the calculations and you get the values here. Again, I've left unchanged. How do I choose 1.2 volt? Alright, we'll bother about it later on. How do I decide on 1.2? Okay, but assuming that you know 1.2, then this is how you would do the design here. Expected swing is only 0.77 volt. Right? So remember the last example? The last example that we saw, what was the swing that we said? That we could get 1.4 volt swing. Right? Now I'm saying with 5% distortion, all that I can hope is 0.77. That's all. And if you make it even lower, your expected swing will be even lower. But also note, where is your bias point? It's not in the middle. Middle point was 3.3 divided by 2, which is 1.6 or so. Remember, our middle point was 1.9, I think we had biased it. Now, the optimum biasing point is 1.38. So all that you read, in this elementary textbooks, bias it in the middle. That's not true. Don't bias it in the middle. If you have, but I'll come to that. When should you bias it in the middle? I'll come to that. There's a reason why you may still want to bias in the middle. So if you have a single one-stage amplifier like this, you should bias it at 1.38. And that, let's see, now let's simulate it again and let's see how well does this work. Okay. Now, if, note that I'm going to get a swing of, 0.77 volt. So I know now, and my gain is how much I can calculate what is the gain. So I know how much input voltage I can apply. And input voltage I can also calculate using this. Vin equal to HD2 by 225 VD-SAT 0.102. Anyway, so let me show you the simulation result. So I've applied 0.102, lower amplitude 0.8, negative amplitude 0.68. What was I promising? 0.77. But remember what this 0.77. It's assuming that it's a perfect sinusoid, right? So it's not going to be, you're not going to get this and this as the same because it's distorted. Distortion means that the positive swing is going to be different from negative swing. So if this is 0.68 and this is 0.8, if you take the average, it's close to 0.77. So it's reasonably close to what we actually are getting. Okay. We are saying we'll get about 0.77, and which is same, 0.68 here, 0.88 here, somewhere in the middle is what you get. Okay. These are, for example, you can, all of you, I think all of you, what you should do is, besides the lab where you're going to use Mentor graphics too, okay, and for your homework and other things, what you guys can do is, there's a tool called MicroCap. Okay, MicroCap simulation tool, and you can go on Google MicroCap, and there's a demo version which is freely available. You can download and install, and demo version is good enough for all our needs. It would allow you something like 50 components or something. You're not going to make any amplifier larger than 50 transistors or so. So it's good enough for all your at least 610 and all these needs here. So any of the circuits that I'm talking about, all these circuits that you see here, and all simulation results that I put here, they're all derived from MicroCap-based simulations. So if you want to verify and, if you want to study some amplifier in more detail, download this software and make this particular design. Circuit is very easy to make. I'll post some tutorials for you, and you can generate all of these results. Okay. Now, this interesting thing is, this particular software also allows us to take this and calculate harmonic distortion. Okay, so that's what I've done. Look at the simulation results. This is my fundamental here, and then it's telling me all the harmonics that are there. And this is telling me total harmonic distortion. So total harmonic distortion is telling me 4%. So I'm getting a swing of how much? You can see here, average of 0.68 and 0.8 at a harmonic distortion less than 5% of this much. Okay. Let's take another example. Let's see, what am I doing here? Yes.
According to theory, we should have had only second order harmonic distortion.
Second order harmonic distortion.
Yeah,
yes.
But this is because we are using Beeson-3 model rather than.
Yes. So it's not a square only. It's not a square only. Okay. So this is another design which is being done for HD2 equal to 2%. Same set of calculations here. Note that what I want to emphasize is, if HD equal to 2%, look at where the optimum biasing point is. 0.98. Very different. 0.98 here. The swing that you will get is only 0.37. Let's simulate it again. 0.35, 0.38. They will always be different. Keep that in mind. Positive swing will always be different from negative swing. That's the meaning of distortion. How much different will depend on how large the distortion is. Run the simulation here. Total harmonic distortion is 2%. Less than 2, you can see here. This is the line here for 2. It's less than 2%. So now, based on those expressions that I gave you, now if you do the design, the design will match pretty well with what you simulate. Okay, because you're taking harmonic distortion into account. All right, so this is a sort of a summary here about voltage swing. These are the different limits on voltage swing here. As I said, this limit, so first limit and the second limit, and based on that you decide what is the swing that you get. All right, now look at this particular figure here for a moment. Now here what I've done is, this is the amplifier that I'm interested in, okay? Remember the same common source amplifier that we are studying? This amplifier here with, this resistance is not important, don't worry about it. Bias is there and all of that, okay? And the statement that I'm making is, you should bias it depending on the swing that you want, depending on how much distortion you want, and you should accordingly bias it. So sometimes an amplifier that you see here will be used as a standalone amplifier, right? But at other times what will happen is, this amplifier, common source amplifier that you see, will be embedded in a larger amplifier. You can see here, this is my common source amplifier. Before that there is some stage, after that there is some stage, right? It's a part of a large multi-stage amplifier. And now in a multi-stage amplifiers, typically what we may do is, we may put negative feedback. We may put negative feedback. Think of this now as a, let's say your common source amplifier as a part of an op-amp. In an op-amp, what will you have first stage? A differential pair. Output stage may be something else, maybe class A, B, class B stages and all that you might have heard of. So it's a multi-stage amplifier, right? And in a multi-stage amplifier, you put feedback. Can you recognize this feedback, R1, R2? You know, inverting in an op-amp, when you make an inverting amplifier, what do? Same R1, R2, right? Feedback you put here. Remember this amplifier is there, minus, plus. You put here R1, you put here R2 and all of that. So that's a feedback that has been done. Now, as I said, if this is my amplifier here, now look at carefully. I have an input stage. Input stage, I've not drawn what this input stage is, doesn't matter. Suppose it has a gain of 10 to the power 3. This is my amplifier of interest. Amplifier where I'm focusing my interest. That has a gain, let's say a factor of 10. 10 is what we had calculated. This is followed by an output stage. Let's say it's a common grain amplifier or something of that sort, which has a gain of 1. Right? So overall the amplifier has a gain of 10 to the power 4. It's looking like an op-amp now. And whole amplifier has a gain of 10 to the power 4. Now who will decide the swing of the amplifier? See this, no, but note that the gain is 1. So whatever swing I will get here, the same swing I will get there. Right? So I should worry about the swing of my common source amplifier. Now the issue is, should I now, if I want a harmonic distortion of whatever, 5% or so, should I bias it at 1.3 or so? Is that how I should design? All those things that I talked about, that I should bias it at this point depending on the harmonic distortion. Is that valid here now? Yes or no? Yes? The answer is no, because I have feedback. What does feedback do? Try to recall what are the effects of feedback. Gain reduces, alright. What else? Input resistance, output resistance get modified, bandwidth gets modified. Huh? Distortion? Distortion reduces. Distortion, negative feedback can drastically reduce distortion. Let me show you now what is happening here. Okay. Let's see the results here. So V0 by Vin is nothing but an inverting, like an amplifier, R2 by R1. Okay. So I have my design of 70K. Based on this 70K here design, this is biased at 1.9 and here, and this is for the whole amplifier. For the whole amplifier, see this. Remember we had biased it at 1.9. And as I had said, without bothering about distortion, I should get 1.4 here and 1.4 here. Right? I should get that. But I was not getting when I take a standalone amplifier. Now I take the same amplifier, embed it in a feedback loop, and look at the result. 1.4, 1.4. Perfect. All that harmonic distortion which is there in this amplifier has all been suppressed by the negative feedback. Now it makes sense to put it in the middle. If I didn't put it in the middle, what would have happened? See, it can't violate this limit. No, it can't go above 3.3. Then I would have lost swing. Now what happens is, so when I said I take a common source amplifier as a standalone amplifier, I have to worry about its harmonic distortion. But when I take the same amplifier, embed it in a larger amplifier and use negative feedback is getting rid of harmonic distortion. And therefore, harmonic distortion is no longer an issue. Now, recall what is happening here. If you look at my overall amplifier has a gain of how much? 10 to the power 4. But this inverting amplifier that I've built has how much gain? 10. So now, you are reducing the open loop gain is 10 to the power 4. Closed loop gain is 10. You're reducing it by a factor of 1000. Now, when you reduce something by a factor of 1000, what happens is, you get benefits of the order of 1000 also. You know, you'll find input resistance will increase by 1000 or output resistance will decrease by 1000. Bandwidth will increase by 1000. So this is all, you know, that's what happens in analog circuit design. Typically, what you do is you're getting characteristics which are not good. So what you do is you make a large gain amplifier. You make a large gain amplifier, then you put negative feedback and you sacrifice all the gain that you've done. You built 100,000 gain, 100,000, 1 lakh, whatever gain. Now you sacrifice it and use gain of only 100. But then as you sacrifice it, you get all those benefits that you see. Input resistance will become large, output resistance will become small, distortion disappears, all those benefits that you get. So that's the strategy that we use in analog circuits. So even though your interest may be in building an amplifier with a gain of 10, right? So if I used a single stage amplifier, gain of 10, you would have never gotten a 1.4 volt swing. Say you want to build an amplifier with a gain of 10. As I just showed you, if you use a common source amplifier, you would never get a swing of 1.4 because it will be heavily distorted. So if somebody asks you for an amplifier with a swing of 1.4 and a gain of 10, what will you have to do? You'll have to go to this complicated solution. You'll have to go to this complicated solution. Build a large multi-stage amplifier, put a negative feedback. You are getting a gain of 10, but now you'll get a perfect swing. Look at how good this amplifier is. Exactly 1.4 and 1.4. Of course, there'll be maybe in second or third decimal place, there'll be some change. But then the issue is how does negative feedback reduce distortion? What does it do?
At the input on the input earlier you were saying and you were sending the input sinusoidal will be distorted.
So that's look at that. If I put 1.3, so the point is, the biasing should be, as you can see here, I should bias it in the middle. If I bias it at 1.3, the swing then is accordingly a problem. Or let me show you here what is happening. Let me go back here. Yes. How is distortion avoided? So you can see that what is happening is as follows here. If you look at VI, the input here, look at VI. We know that as I go from VI to V0, distortion occurs, right? When I go from VI to V0, the signal is getting distorted. So what my negative feedback is doing is distorting VI itself. Look at what VI is. VI is heavily distorted. Such that, so it distorts it in such a way that then as it goes through the amplifier, it gets distorted in the opposite manner and what comes out is a perfect sinusoid. That's what negative feedback is doing. Okay? It's distorting the sinusoid itself, the input to this amplifier. So, these are more realistic cases and all that. So I have here. So the message is, what if I have a standalone amplifier? I have to worry about is harmonic distortion and the swing and all that we calculated is required. That's how you would design. But if you're going to take this amplifier, embed it in a feedback loop, then you go ahead and bias it in the middle, and that should be fine.
Sir, is this also a very good technique for noise reduction?
What? Feedback is helps in noise reduction also. Yes.
Sir,
yes.
How much distortion can tolerate?
It depends on how much you see from how much decrease in gain you carry out from closed loop gain and the open loop gain. How much is the difference between the two? Say if what happens is my open loop gain is, let's say, 10,000, and if I build an amplifier with a closed loop gain which is say 5,000, so the decrease will not be that much. But now I built an amplifier with a gain of 10. So I'm sacrificing gain a lot. So therefore my distortion also becomes less. So these things are related together. Okay. Again, what I would suggest is make this particular circuit in microcap and go ahead and experiment and see what happens here. Build this R1 and R2 and all that change and see how things are changing. Okay. Yes. Yes, frequency. So right now I'm not, the gain will depend on the frequency. Yes, the gain will depend on the frequency. So what happens is, as you go to higher frequencies, the overall gain of the amplifier drops, open loop gain drops significantly, and that may have an effect on the distortion also.
And so the bandwidth of the circuit will be down with each of the
Okay, bandwidth is where we are. That's the next the topic is what we have to discuss. So that was a discussion related to harmonic distortion and voltage swing. The next important point is frequency response. Frequency response, all of you have seen this graph here, which where is shown gain versus frequency. So there's a region where gain is flat, and then the gain drops at higher frequencies. Gain may, I'm using the word, I'm saying gain will drop at higher frequencies. Gain may drop at lower frequencies or may not. That depends on the kind of circuit that you have here. Okay, and this part comes about because of external capacitors. This part comes about because of all the internal capacitors, transistor capacitors. If you don't connect any external capacitance, then your gain is going to be flat right up to 0 frequency. And we call these amplifiers also as DC amplifiers. They can amplify DC also. Okay. Mid-frequency region is where we can ignore, since gain is not varying as a function of frequency, which means capacitors don't matter. So you can remove all the capacitors. Okay, so very quickly, how do we calculate the upper cutoff frequency? Well, if we want to calculate, so we are interested in calculating this one. Upper 3 dB upper cutoff frequency here. So we have to substitute now all the full high frequency bond with all the capacitances that you see here. CGS, you see here, CGD, C drain to body. Just for the sake of completeness, I've added, let's say there's a load capacitor also, CL, and input can have its own capacitor also. Input I've put VS and RS, and input can also be associated with some capacitor, CS here. Okay, just for the sake of generality here. So you have a circuit like this. How do I find its 3 dB frequency? What is the general method? What should I do? No, that we know. But now I have a circuit. So what should I do? Transfer function, right? I should write down the transfer function and then from the transfer function plot it out and see. Okay, so let's write down the transfer function. Transfer function, I'm not going to sit down and derive for you, but if you do that, transfer function will come out to be of this kind. It's you can see a second order system. So you get a quadratic, this thing in the denominator, which indicates what? 2 poles. 2 poles are there, and this indicates 1, 0. So a common source amplifier, the simplest common source amplifier that you see here, will have 2 poles and a 0. Okay? These are the values. G equal to so much, H is so much here, and all the expressions are in front of you. Okay? Now, how do I find the 3 dB from here? Say, after, you will require maybe half a page or 1 page to fill it up, to do this. So you get this expression. How do you find 3 dB? No, I need an expression of 3 dB, right? Magnitude is fine. Then I would put in there and calculate magnitude. But what if I need an expression? Expression for 3 dB. Because expression will tell me what does my 3 dB frequency depend on. I'm not looking for a number, a numerical number. I'm looking for an expression. So what do? I have a 0, I have 2 poles. And you can see I have a complication here. How do I calculate an expression for 3 dB frequency? It's not straightforward. Numbers I can still numerically I can churn and get some number. But expression, I'm looking for an expression. So we get stuck here. Alright. So as I said, numerically all that you would do is maybe once you have an expression, you can plot it out and you can find out where is 3 dB and calculate whatever. It will take you time, but you can do that. You can calculate what the 3 dB frequencies will come out to be 0.43. But we want an expression. Well, what we can do is, we can write the whole thing in this form. Let's say two poles are there, wherever they are, one j omega by omega 1, one j omega by omega 2, j omega by omega 3 here. Now, this is where, because I'm looking for an expression, assumptions come into picture. And the assumption, this all of you already know, the assumption is as follows. Most of the expressions for 3dB will be based on this expression, this assumption here. And the assumption is, I have a dominant pole. I have a dominant pole in my system. So we are saying is, let's say omega 2 is much, much larger than omega 1, which means my dominant pole is omega 1. Not only that, I'm saying my dominant pole is at a much lower frequency than my 0 also. So this assumption is being made. Whoever is giving you an expression for a 3 dB frequency is making that expression, making those assumptions usually. That I have a dominant pole in the system. Once you say I have a dominant pole in the system, then you can say, well, my omega 3 dB is approximately equal to omega 1, the dominant pole. Okay? So let's see. So this is the expression that I have. So what I'm going to do is the following. Note, 1 plus G that you see here, I write it as 1 minus S by P1, 1 minus S by P2. Two poles are there. We write it like this here. Okay? Expanded. And now, P1 is the dominant pole. So I write 1 minus S by P1 plus S square. I keep this S square P1, P2. Now you can see that it's easy for me to determine the dominant pole. P1 will be simply equal to 1 by G. And once I know P1, 1 by G, P1, P2 is 1 by H. So I will know P2 also. So I will quickly obtain an estimate for P1 and P2, assuming a dominant pole. Alright, so this is what is being done. P1 is 1 by G, P1, P2 is so much, and then one obtains that. Yeah. Now, once you do that, please go ahead and check, is my P2 at least a factor of 10 larger than P1 or not? If it is true, then your assumption is correct. You are under a dominant pole approximation, and your expression for 3 dB and all that is fine. If not, then the expression is going to be problematic here. So, with that assumption, with that in mind, that I have a dominant pole in my system, which is P1, we obtain an expression for 3. F3 dB is 1 by 2 pi RS, EGS, EGD, and all that, which is simply from G. It's simply equal to G, and we have a expression which is valid. Okay. The second pole is here, and then one can. So that's a general way of doing it. General way of doing, meaning you derive a transfer function, and from the transfer function, make an assumption of a dominant pole, get P1 and P2, and you will also have a 0 also. Make sure that P1 is much smaller than both P2 as well as the 0. And if that is true, then you have an expression which is valid for you. And then you can use it for understanding how the amplifier behaves. At many places you will find this will get violated. Especially I want to warn you that when you go to common drain amplifier, you will find that this assumption will not be true. Common drain amplifiers. The dominant pole, the kind of a assumption doesn't go true here. But in common source amplifier, you will find it's not a bad approximation. So that's one way of doing it. Another way that all of you know is open circuit time constant approach. Where what do? You say F3 dB, this is the approach that we are going to use throughout our course. We will say F3 dB is 1 by 2 pi sigma tau. Tau. Now tau is equal to associated with each capacitor. So what we are saying is each capacitor is associated with a time constant. And what is the time constant? Tau j is equal to Rj times Cj. And where Rj is the effective resistance seen by the capacitor when all other capacitors are removed from the circuit. Removed means open circuit. That's why the open circuit time constant. So we have a simplified approach where we are saying, and one can show that where this particular equation is coming from, but I'll not bother here. So F3 dB is, there should be a big approximate sign here, 1 by 2 pi sigma tau. And all that we need to determine is time constant associated with each capacitor. Okay? So, for example, what is the 3 dB of this one? Using open circuit time constant, what will I do? Well, consider C1 first. So I'm going to open circuit C2. Just to remind you, C1 is here. What is the net resistance seen by C1? How do I do that? I remove the source. And net resistance seen by C1 will be? Well, here it's very easy. this one is in parallel, this one is there, you can easily write it down. But if you can't see it directly, what do? You put a source Vx, and there's a current Ix that the source gives you, Vx by Ix will give you the resistance seen by your capacitor. Right? So you calculate this one here, so that gives you time constant C1 RQ1. Similarly, consider C2, calculate this time constant, so it's here, R2, calculate the overall 3 dB frequency, 1 by 2 pi, the sum of the two time constants here. And that's the approach that you use, okay, for calculating. So same thing you will use here. So you can verify. If I use CGS as the first one, what is the source? What is the resistance seen by CGS? RS straight. So CGS times RS here. What is the resistance seen by CDB? Drain to body. Can you see now? There's no source. If there's no source, then the current source is open. So it's simply equal to, which is basically equal to RD. More complication occurs with CGD. What is that's why I said, what is the resistance seen by CGD? It's not straightforward. You can't simply write it. So now in this case, what you do is you remove CGD, put Vx, look at Ix, and solve this simple circuit. Okay, solve this simple circuit, and you'll find R effective is RS1 plus GMRD plus R. So this is the resistance seen by CGD. And now you sum up all this thing here, and you get a 3 dB frequency, which matches exactly with the dominant pole. The dominant pole is also giving you the same thing. Okay, so this open circuit time constant approach is also making the assumption of a dominant pole and calculating it 3 dB frequency based on that. Another thing that you have to keep in mind, so for some capacitors that you see here, the calculations are very simple. For other, especially a capacitor which is connected between input and output, the calculation becomes more complex. This is where Miller's effect comes into picture. Miller's effect, as all of you know, what it will do is, if there's a capacitor connected between input and output, it will break the capacitor into two, one connected entirely at the input, one connected entirely at the output. And then we can apply the same open circuit time constant approach and get the expression. So it will become even simpler. Right? So let me stop here. I think there's already too much. So we'll continue. Okay.